You so much. Okay, I'm gonna start. If there's any questions, I can't really see the chat too great, so I'll look occasionally. But let's begin. So, hello everyone. My name is Ryan Godin, and I'm a master's student with the University of Sherbrooke in collaboration with Agriculture and Agri-Food Canada. Today, I will be introducing what quantum machine learning is and why we believe it to be an important topic in today's quantum race. So as I said, my name is Ryan Godin, and I just recently finished my bachelor's degree in astrophysics at the University of Waterloo, and now I'm working towards my master's at UDS with Dr. Nadia Tahiri. And for the last year and a half, I've also been working on a quantum machine learning project with Agriculture Canada under supervision of Dr. Etienne Lord, where we work towards applications of QML in agriculture. And I'll also provide some references regarding this topic if you're interested in learning about more or how to do it yourself. So over the next 45 minutes-ish, I want to give you some background information on what quantum computing is, then transition into how we use it in machine learning methods, and elaborate on why we believe QML has the potential to provide the desired quantum computational speedups we expect from quantum computing. Then we can discuss shortly where QML falls short and where it can be applied. So, quantum mechanics. This is an introduction that should give you some background information on what quantum is and how we leverage its unique nature. So, quantum mechanics is typically used to describe small physical interactions, such as atoms interacting with the electromagnetic spectrum, or the way electrons spin and interact with other electrons. Um, so classical mechanics is a language we use to describe the motion of macroscopic objects. In classical mechanics, we can determine the outcome of a system if we have enough information about how it starts. Quantum mechanics is a language that describes the probabilistic nature of these things. However, in quantum mechanics, there is no way to determine the outcome until we see it. Like classical mechanics, quantum mechanics has its own special rules, and these rules are what make quantum objects so interesting and useful. The first is entanglement, which is also known as spooky action at a distance. Then we have superposition, and last we have interference, which governs the interactions between two quantum systems. There are other rules in quantum mechanics which are really useful, but these are the big three for today's presentation. So what is entanglement? An example of entanglement is you just bought a pair of gloves. You put both gloves in separate boxes and send one of the boxes far, far away. If you open the box you kept and it has the left glove, you immediately know that the other box has the right glove. This same principle works for all entangled particles, like an electron's up and down spin. Of course, the gloves are more of a representation of what entanglement is and are not really entangled. This rule is how we use quantum computers to achieve their exponential power and correlated behavior and communication / teleportation of information. The other very important rule is superposition, which most of you are already familiar with. Schrodinger's cat is an example of superposition. If I put a cat in a box and it has a 50% chance of it dying by using some material which has a 50% chance of decaying or becoming radioactive, if I don't open the box, is the cat dead or alive? Why not both? Of course, we know whether the cat is dead or alive when we open the box, when the probability wave or the wave function collapses onto one of the options. This rule is behind quantum computers' massive parallelism, giving quantum computers the ability to explore more than one option at once. The third rule is interference. And interference is the act of two different waves interacting with each other, both constructively or deconstructively. In quantum mechanics, you can think of this as using the double slit experiment. A photon or electron or any quantum object is passed through two slits and then is detected on a wall behind it. If you were to pass light through the two slits, you would expect to see two distinct bars where the light passes. But light or photons have this unique quantum property, and it causes the light to behave like a wave. The two waves from the slits interfere with each other, causing that distinct pattern of constructive, the bright spots on the wall, or deconstructive, the dark spots on the wall. This is helpful in quantum computing because we use it to amplify our correct results and we use the deconstructive waves to cancel out our wrong results. So this leads me to quantum information. So what is a bit? Most of you may already be familiar with bits. They're in every single piece of electronics you own. Classical bits store information by using ones and zeros, acting as a command to a physical circuit. Classical bits store information, oh sorry, where zero tells us whether to turn a transistor or a switch on or off, and only ever these two options, making them deterministic. Bits store information by converting them into zeros and ones. Take, for example, my name. To store 4 letters in UTF-8 encoding, you need 32 zeros or ones, or 32 bits. So what if I could store my name using less information? Well, that's exactly what quantum physicists said when discovering the power of quantum bits, aka qubits. Qubits are at the core of all quantum computing processes. And qubits physically act like classical bits, but rather than being 0 or 1, they can be a mixture of the two states. You can think of this like the cat in the box. If the cat is dead, the state is 0. If the cat is alive, the state is 1. We can put the cat in the box and close it, and it becomes this zombie cat, or some mixture of both states. These unique quantum principles help us create efficient algorithms, as I mentioned before. Qubits are physical things, for example, electrons, and electrons behave quantum mechanically and are perfect example of how we can create a qubit. So what is a quantum computer? A quantum computer isn't how you might perceive it. In this image, you see a lot of cables and pipes and a lot of metal components, but none of these are the actual qubits. Most of what you see is one really large refrigerator with one goal: keep the qubits cold and isolated. For us, to use qubits and control them, we need to ensure they are stable and don't interact with heat, which will excite them and cause them to lose their state, meaning we lose information. Another portion of the quantum computer is designated to controlling the state of a qubit. Each quantum computer is different and is a very active area of research. So quantum physicists have been exploring a bunch of different ways to create qubits, using different quantum objects. Some use light, some use electrons, but the most promising so far is using superconducting ions or superconducting circuits. And so each different type of qubit requires a slightly different design of quantum computer. And we are far from having something to sit on your desk. So I won't talk too much about the physical quantum computers, but to provide some reference as to the physical hardware, here's some images of Google's quantum computer. The image on the left shows what most quantum superconducting computers look like. A significant portion of the design is used for cooling and maintaining the quantum chip on the right. The image on the right you can think of as the CPU of the quantum computers. And for most current day quantum computers, these chips have around 105 practical qubits, like the one in Google's Willow quantum computer, which is the one I showed. These massive computers aren't like traditional computers. They're in a very new stage of development and are consistently being improved. Within these quantum computers, qubits must be maintained at temperatures colder than deep interstellar space, so as close to 0 Kelvin as possible. And due to this, real physical quantum computers fall short in several areas in current day research and have a long way to go before, they're in your hand or in everyone's desk or office. So in quantum mechanics, we use Dirac notation or Bra-Ket notation to simplify the linear algebra notation for these large state spaces. These fancy brackets you are seeing are just representations for operators and inner products in dual vectors. For example, we have the 0 state represented by a vector 0, 1, and our 1 state represented by 1, 0. By using this notation, we can easily express probability. Take, for example, the 1 qubit system, like our electron. We can have the 0 state and the 1 state, or some mixture of both states, where the sine theta and cos theta represent some probability. This notation is extremely important in expressing systems, and it gets a little bit more complicated the more qubits we have, but allows us to store more information. Like, for example, my name again. we could represent it using 2 qubits instead of 32 classical bits. The amount of information we can store depends on the number of states we have, which increases exponentially with the number of qubits. So how do we control these states? We use quantum gates. Quantum mechanics is just a bunch of linear algebra, which we use to describe quantum states. These states can be changed using operators mathematically, which are just matrices which we inner product onto the state. These operators perform various changes onto our state to do what we want. To list a few, the Hadamard gate, which introduces superposition, the Pauli XYZ rotation and phase gates introduce superposition and interference. CNOT gates introduce entanglement, and swap gates introduce teleportation of information. So to describe these a little bit more, a Hadamard gate puts our quantum state into superposition, like putting the cat into a box. For example, in this image, we have the 0 state, and then a Hadamard gate is acted onto the state, which turns the state into a 50% chance of it being 0 and a 50% chance of it being 1. And right in the middle of these two states. The rotational gates in quantum mechanics work similar to the Hadamard gate, but rather than simply putting the qubit into superposition, we can control how likely it will be in the 1 or 0 state when we measure it, aka opening the box. In this example, I'm rotating the state around the x-axis. However, we can also rotate around the y-axis and the z-axis to achieve things like interference. C-naught gates are the last I will demonstrate, as after this, the math becomes a little too ugly to look at. And so the C-naught gate, aka the controlled NOT gates, are the main tool we use in quantum computing to introduce entanglement into the state. If I have 2 qubits, one starting in the 0 position and the other starting in the 1 position, we can tell these 2 qubits to perform a bit flip, working like its classical counterpart. By entangling these 2 particles, we can transfer information instantly, which provides us with that computational speed up. And so throughout these slides, you've seen a bit of math. Most of these are just to show you that everything we do in quantum computing is just some form of linear algebra, as I promised earlier. So the rotational gates in quantum mechanics work similar to the Hadamard gate. Oh, sorry. This is the same slide for some reason. Okay. Quantum circuits are the main focus for quantum software developers. Similar to classical computers, to change bits, we need some sort of logic in place to tell the computer to flip or shift bits at certain times. However, in quantum computers, uh, we're not expecting to replace them exactly, but they have been proven to be better at some tasks. Shor's algorithm is an example of a quantum circuit which can factorize numbers more efficiently than a classical computer. Grover's algorithm is really good at searching through databases or solving mazes because it uses the quantum nature to check multiple paths at once. And then there's also quantum Fourier transforms, which have been proven to be faster than a classical Fourier fast transform. And I demonstrate an example of what the quantum Fourier transform looks like in the circuit. And it's just using some gates that we just discussed. Showcasing how these gates come together and are placed to complete some circuit or algorithm is kind of the core of quantum computing. So how do we use quantum? So you might be wondering how we run all of these circuits. Well, you're in luck. You don't need to be a millionaire with access to cutting edge scientific equipment and a team of quantum computing engineers. Companies like IBM, Xandu, NVIDIA have made it possible to test your ideas and quantum algorithms by simulating quantum probabilities using platforms like Qiskit, Circuit, PennyLane, or Qt-Quantum, to list a few. Most of these software development kits, or SDKs, can be run on Python or C++ and make it easy to develop quantum circuits and algorithms and scripts before testing them on real quantum computers. To create these circuits, if you know what you're making, it's as easy as the code I've shown here. This example is just meant to show you a few of the possible gates you can use and how easy it is to construct these circuits. Additionally, certain companies like IBM have publicly available real quantum computers, which you can submit these exact codes to and test on real quantum computers. However, these computers have a lot of noise and low coherence times, meaning information is lost very frequently. In today's current state, quantum computers have a long way to go before being able to efficiently run code with little to no information loss. Until then, us quantum software developers will keep focusing on error correction code and improving algorithms to minimize the computational costs of current state quantum computers. So, quantum machining, which is the main portion of my presentation. So, why do we use quantum machine learning? Or, yeah. So, quantum computing has proven it can be a successful method for specific tasks. Mathematically, we can demonstrate the computational costs, the complexity reductions, and the time speedups provided from these algorithms. But quantum's unique nature also provides us the ability to express data in a new way. Quantum machine learning benefits from something known as the Hilbert space. In its simplest form, it's just some n-dimensionally large space, which increases with the number of qubits within a system. In classical computing, most data or information is stored in some linear manner. And to introduce nonlinearity into the system, we use functions like the ReLU function and sigmoid function. For a quantum model, however, the Hilbert space allows this data to be encoded nonlinearly and enables us to express relationships between data points easier. With this, any high dimensional, nonlinear, or classically hard data becomes easily represented using the Hilbert space. For example, we can take hyperspectral data, which can be very complex to store and represent. With our quantum tools like the Hilbert space, this data becomes easily expressed, and this is the exact motivation behind quantum machine learning. So, what does all this Hilbert space nonsense mean? With more expressive data representations, quantum machine learning models will be able to train faster, with less data, and potentially with increased accuracy. So, what is machine learning? I'm assuming most of you are familiar with some machine learning processes. However, in this slide, it's just to clarify some representation. So, for some real data X in a data set large X and its associated labels Y, we create a function which maps the data X to its appropriate label. This is typically done by weighting or optimizing parameters within the green portion of the diagram. By optimizing a loss function, we can tell the neural network which parameters and which characteristics are important within the data set, ultimately ending with some sort of appropriate classification of data. There are a significant number of machine learning models, including neural networks, which I will focus on, support vector machines, k-nearest neighbor, and regression models. Each model follows a very similar process, but have different use cases depending on the goals and data that you're using. For example, linear regression models are really good at creating relationships between dependent and independent variables by finding a best fit linear equation, which shows the relationship of these two. But linear regression isn't great when working with classifying image data. So, what is quantum machine learning? Quantum machine learning works in a very similar way as classical machine learning, ideally with some data X classifying into Y labels. The main portion of the neural network is now replaced with a quantum circuit consisting of two main parts. The first part is an encoding circuit. This circuit takes the inputted X data and converts it into a quantum state, which can be passed through our quantum circuit. And the second portion of the circuit is the ansatz. And the ansatz is a parameterized circuit, which will be optimized by the loss function. The ansatz typically consists of rotational gates and can control the quantum state and the resulting output when we measure these states. For most quantum machine learning models, a classical model is used to solve the cost landscape because the problem itself is a deterministic problem, which classical computers are already really great at doing. So there's no need to reinvent the wheel on that. So quantum neural network model. So as I just said, to reiterate, the encoding portion of the QML model, the quantum machine learning model, takes normal classical data, or sometimes quantum data if you're using it, and converts it into some defined quantum representation. This can be done in several different ways, and depending on the data that you have and how you want to represent it. We can use amplitude encoding, which directly changes the probability of the outcome by changing the wave function by increasing or decreasing its amplitude. Then there is basis encoding, and basis encoding basically takes your array of data and encodes it directly onto the desired or matching state. This works well for small binary data and makes the conversion from classical to quantum easily understandable. The next is my personal favorite, which is rotational or angle encoding. And this is done by rotating some state around the feature space using rotational gates, as we mentioned before. By normalizing data between 0 and 1, these values can be encoded as some rotation around the x-axis, y-axis, and z-axis, thus changing the probability of the output states. And there are several other methods which I won't go into. However, for all methods, it's important that you represent your data appropriately. Too many parameters or high expression, and you can overfit your data, and not enough parameters or low expression, and you may underfit your data. Additionally, it's important to remember that the more qubits you use to encode data, the noisier your results will be, and information will be lost. It's important to consider these trade-offs when creating any quantum algorithm. So, like classical neural networks, it is required to have some circuit which can be optimized by the loss landscape. These are typically called ansat circuits and can be some arbitrary mixture of both parameterized rotational gates and some entanglement structure. For most machine learning models, the parameterized rotational gates are just some gate RZ, RY, or RX, which are again just some operator that we act onto the quantum state. For the entanglement structure, there are various options you can pick from. In this image that I've shown, we just use a linear. So we connect each qubit to its nearest neighbor, and then we circle it back to the top. So all the information is kind of connected in some manner using the entanglement. And there are many different options for selecting these depending on your goals and data. There are also other ansatz designs, such as the convolutional ansatz or the pooling layers, which researchers have demonstrated are also possible for creating convolutional neural networks. And so it's important that your design matches the classical version you're comparing it to. And so I've mentioned that we always focus on reducing the number of qubits that we use uh, when we create any quantum circuit, and I will demonstrate this near the end. So once the data has moved through our quantum circuit, we need to obtain the quantum results and convert them into classical usable results for our quantum computer process to process. We do this by measuring the final output state 1,000 times. Typically, these are called shots, and you can think of these like opening the box 10,000 times and finding the cat dead about 50% of the time and alive 50% of the rest of the time. However, with our circuits, we can control the probability, like what I've shown in this image on the right. I designed a quantum circuit so that only some of the states would be probable. In this example, the 1000 state and the 0100 state are the most probable. This is the goal of quantum machine learning. Certain data points will map to certain states depending on how the circuit changes as you progress with your machine learning model by optimizing these parameters within the ansatz. We make these states appear more frequently and correctly label the data. So the classical training loop works similar to an average machine learning model. The bit strings from the measurement results is converted to some class probability and remapped onto each label. The predicted labels are then compared to the true labels to determine the loss landscape. The classical computer will then navigate this cost landscape and reevaluate the parameters within the ansatz, which again are just some rotation around the X, Y, Z axis. The full process can be seen in this image where the data enters into the feature map, converts it into a quantum state, which is then passed into our ansats and measured and mapped onto the Y labels. This hybrid classical quantum model has shown some promising results for specific sets of data and is still a very active area of research. So there are several different machine learning models which are used for various tasks. To list a few of them, quantum k-means, which groups data together based on some quantum distance metric, whether that's the position within a Hilbert space or rotational metrics. Variational quantum classifiers is similar to the neural networks, utilizing some classical optimization on a parameterized quantum circuit for supervised learning. And then quantum support vector classifiers are quantum kernel estimators, which are used to compute similarities in high dimensional Hilbert spaces or feature spaces for classification or regression. We also have quantum neural networks, which are well defined at this point in this presentation. And then there's quantum autoencoders, which work like classical autoencoders with the primary goal of reducing the dimensionality of data with minimal information loss. And these are just a few of the models that researchers are currently working on. And most of these are based on some classical counterpart where the majority of the classical deep learning network is replaced with some quantum circuit to provide improvements to its design. So I provided some really great Python resources here for you to learn how to code yourself and to make these quantum circuits. And I've used and I still use a lot of these myself to learn quantum computing and quantum machine learning. The internet is really just a magical place sometimes. So the first link is a tool to help you understand what is happening to the qubit when you apply gates to it. So if any of my description of the gates confused you, I would really recommend go check out this link. The second is some basic introduction into coding using Circuit or CirQ, provided by Google's quantum team. And this is really great for learning how to code and what you can do with current state quantum software development kits. The third link is an example to where you can create quantum algorithms, which are better than its classical counterpart. So the CHSH inequality problem is this problem where we show the quantum version of it is better than the classical version. So this is a really great link if you want to see that demonstrated. And the last link is a tutorial for those looking for something a little bit more challenging and interested in the quantum machine learning methods. I will send all of these links into the chat after. I just don't want to close this presentation by accident, so I will copy and paste them after this, or you can screenshot the slide. Okay. So there are a few current issues with current day quantum computers and quantum computing. So as I mentioned before, when working with current day quantum computers, we must focus on decreasing the number of qubits we use to express data or create an algorithm. This is because the longer we demand a qubit to be stable, the more likely it will interact with its environment and lose the state we want it to have, aka lose information. These environmental interactions can be several different things, including thermal noise, vibrations, interactions with other atoms in the system. And so there is a whole other side of quantum computing dedicated to creating code to correct these errors and helping minimize the effects of this decoherence. Additionally, for most quantum simulators and real quantum computers, it is only possible or realistic to simulate around 32 qubits, whether due to physical limitations of current hardware or the computational resources that are available to you. However, in time, this number will increase with, better hardware, better computers. So this concept is kind of hard to understand without an example. On the right, I created two different gradient images. One is a 2x2 and the other is a 4x4. I then convert these two images into quantum states and then pass them through a real quantum computer. The 2x2 image used 3 qubits, where the 4x4 qubit used 5 qubits. I then pass these images through the real quantum computer in Sherbrooke, provided by IBM. And then the result is clear from the images. The top image, or the image that uses less qubits to encode, you can still see the gradient pattern, whereas as I increase the number of qubits, that information or the gradient pattern is kind of lost as I pass it through a real quantum computer. So it's really important to focus on decreasing the number of qubits when creating any algorithm in quantum. So accessibility is another issue in quantum computing. These computers are typically extremely limited, with IBM Q only having around 20 available quantum computers, which you can access for about 1 minute a month for free. Which leads me to my next point. Running code on these quantum computers is extremely costly, which is why it's really important to simulate or emulate quantum circuits using classical computers prior to submitting to these computers. Two of these quantum computers are in Quebec, including the Monarch and the IBM Quantum One computer. In this image, there is a few IBM quantum computers listed, and they provide a lot of information about the specific computer that you're using, including the number of qubits it has total, the readout error, so how much decoherence is in the system, how much information is lost on average. And it also tells you which qubits your code is running on, which I think is really neat. So what's next? Applications of quantum machine learning, quantum algorithm, and quantum computing in general are being challenged daily. The applications of quantum machine learning are hoped to provide some promising results in various fields and might be a solution to some of the larger issues we face with classical machine learning models, such as computational costs, speed, and hardware usage. So a lot of the recent research activities include agriculture satellite image classification, which is exactly what we do at Agriculture Canada. We take satellite images, pass them into a quantum machine learning model, and we're trying to prove that by doing this, we can represent hyperspectral images or satellite images better than a classical computer can. Some other topics would be phylogenetic clustering algorithms, and there's been a lot of research into security, communication, and cancer research, all using quantum algorithms, quantum computers. That also includes finance, biology, physics, agriculture, and the list really just goes on to any field you can think of applying it. And so there's also a lot of research going into the hardware side of quantum computing. By increasing the number of qubits and increasing the coherence of these qubits, while also exploring different options for quantum computers and trying to figure out which is the best. And on the software side, all of the software developers need to work on error correction codes. Yes. Sorry, I just read the next slide. In many ways, we all feel like Alan Turing. But yeah, that was my presentation. Sorry, I messed up this last slide a little bit. Quantum computing is a very active research domain, and I'm excited to have shared it with you guys. So thank you all, and let me know if you have any questions in the chat. I think I finished a bit early, so.
Thank you, Ryan. It was very interesting talk. So it's a time for the questions. So feel free.